Now today I will show you my favorite research area, and our research is regarding regional groundwater flow systems in the Pannonian Basin, Hungary. Now we are working on this topic with my colleagues in the ELTE József and Erzsébet Tóth endowed hydrogeology chair. So I will talk about regional groundwater flow systems and regional scale pressure regimes. And the practical importance of this topic is come from the question of renewable and non-renewable groundwater flow resources. So I will start with this in my presentation. So I think all of you know that due to the increasing population and climate change, the people are increasingly turning to groundwater resources and also to non-renewable resources. So we have to deal with this question from different point of views. But let's start with the question, what counts as renewable? You know, there are different type of definitions. How can we define renewable or non-renewable resources? Now, from a first look, we can say that groundwaters, as the subsurface part of the water cycle, can be handled globally as a renewable water resource. But of course, from a water management point of view, it can be necessary to separate somehow the renewable and non-renewable groundwater resources. Now here you can see the two most used definitions. We can talk about, or we can define fossil waters, for instance, which are older than 12,000 years. Or in a more severe definition, we can say that we can handle all groundwater resources as non-renewable, which are non-renewable on a human time scale. So these renewability time is longer than 100 years. Now, in the following, you will see that in our interpretation, we will say, or we will use the renewable term for those groundwater resources which has surface recharge areas, so which has connection to the land surface where surface waters or precipitation can infiltrate and feed groundwater flow systems, while I will call the groundwater resources non-renewable, which has no surface recharge area, which has no connection to the land surface, so they cannot feed by the precipitation or other surface waters. Now let's see how can we apply this definition to the different type of groundwater flow systems. Now we know that in all terrestrial sedimentary basins and also outside of the basins, so actually everywhere we can find topography-driven groundwater flow systems from the land surface down to even some kilometer depths. And these flow systems have replenishment. So we know that in the recharge areas, regional, intermediate, and local recharge areas, water can infiltrate into the saturated zone and feed these groundwater flow systems. Now, it will be also important later that in these flow systems, or these flow systems usually represent normal pressure conditions. Now, on the other hand, I would like to talk about the abnormal pressure regimes. These are very interesting for us because in the Pannonian Basin we have overpressured regimes in our deeper sub-basins. So these abnormal pressure regimes, which can be also under-pressured, but in any case, the abnormal pressure regimes can be handled as non-renewable groundwater resources, since these don't have any connection to the land surface, don't have any surface recharge. Actually, we can find that water in these systems, which was let's say, trapped a long time ago. So in the following, I will talk about overpressures, because in Hungary, in the Pannonian Basin, we have overpressures in most of our deep sub-basins. And we wanted to define somehow the upper boundary of the overpressured zone. And you know that there are also different ways how can we define this boundary in the literature. Maybe one of the best known is the dimensionless overpressure parameter of Domenico and Schwartz, which can be defined as the difference of the observed or measured pressure minus the hydrostatic pressure divided by the difference of the lithostatic and the hydrostatic pressures. Later, Haneke Fervey classified these overpressured values and set up these categories from normal through slightly to over and severely overpressured systems. Now, in our case, in generally, we could see that it's usually not easy to define the hydrostatic normal or nominal pressure in a given depth. There can raise a lot of questions regarding, for instance, the density, the water density, or the presence of other fluids, such as hydrocarbons, for instance. And on the other hand, we would rather want to handle this question, as I have shown you in this figure, so when we try to find the boundary of the normal and the abnormal pressure regimes, in this mean, we're not just looking for numbers or quantitative methods, but we talk about these regimes as flow systems or regimes where different driving forces are acting. In the topography-driven system, you know, the topography, or rather the water table elevational differences drives groundwater, while in the abnormal pressure regimes, always some kind of geological forcings drives fluids, but the fluid flow is inhabited in these systems by some low permeability formations, such as this brown layer in this figure. So based on this approach, we find out this method or methodology to define the upper boundary of the overpressure, which is actually define the lower boundary of the topography-driven systems, because we started from the theory, or from the well-known thing what I have already mentioned, that topography-driven systems usually represents the normal pressure conditions or close to hydrostatic pressure conditions. And starting from this fact, we said that if we check the observable or measured hydraulic data, hydraulic heads or pressures in a basin, then within the topography-driven groundwater flow systems, so in the normal pressure regime, the maximum and minimum hydraulic values which could be found can be defined as the maximum and minimum water table elevation in the given basin. So if you know that what is the maximum and what is the minimum elevation of the water table in our basin, then we can define the maximum and minimum hydraulic heads, which can be occurred in the normal pressure system. And if we use these boundary values, for instance, in a hydraulic head versus elevation profile, where we can evaluate or interpret the measured hydraulic head values of wells, the minimum and maximum H values define two vertical lines. Between these two lines, we can find the normal pressure regime. Above the maximum, there is the overpressured regime, and below the minimum, here is the underpressured regime. And in the same way, we can draw these two lines, boundary lines, on a pressure versus elevation profile. Here, the starting point of the lines, boundary lines, will be again the maximum and minimum hydraulic heads, or rather water table elevations, while the gradient of the two lines is the same namely the hydrostatic vertical pressure gradient, which is typical for the given system. Okay, so we use this method to define the upper boundary of the overpressure or the lower boundary of the normal pressure regime in the Great Hungarian Plain part of the Central Pannonian Basin. We worked with about 6,500 hydraulic data from wells. So again, these were water level and pressure data. And here you can see the results on pressure elevation profiles from the different study sites. And the main point is that you can see where the data points starts to deviate from the two boundary lines. These pressure data show us the overpressured regime. We can see also 200% overpressures compared to the normal or hydrostatic values in the really deepest basin parts. And the top of the overpressured regime is around 1,500 or 2,000 meters. It depends on the geological conditions. Okay, now based on these PZ profiles, we can see the normal pressure regime. So let's say the topography-driven systems and the overpressured regime. Then we always use fluid potential maps to evaluate the groundwater flow systems, but now I would like to skip to the hydraulic cross sections, which give us some more information, some very interesting information about the flow systems, because for instance, in this section, you can see that this red dashed line shows the approximate upper boundary of the overpressured system. And this part of the section signed by the purple line show us the actual topography-driven groundwater flow systems, which has a recharge area. So groundwater replenishment in the northeastern part of the study area, and then somewhere around the middle of the section, we can see that the flow lines turns upward, and the discharge area can be found from the middle of the section and in the southwestern half of the section. And what is the new in this interpretation is that between the overpressured system and the topography-driven systems, you can see a quite thick or extensive zone. This is what we call as a transition zone, because on one hand, it showed normal pressure conditions, so we can find the data, the measured data of this transition zone in the same normal pressure condition part of the PZ profiles as the topography-driven systems data. So we cannot differentiate these data based on the PZ or HZ profiles. But we can see from the cross sections, and I now delete the letters. So if you see the groundwater flow directions, we can see upward flow directions everywhere within this transition zone. And this is what helps us to separate the transition zone from the topography-driven system in the recharge areas of the topography-driven systems, where the two zones or systems show opposite groundwater flow directions. Now this, we could interpret this transition zone or this uniform upward groundwater flow as the result of overpressure dissipation. So even if we are in the normal pressure regime, but there is a very small excess pressure which causes the superhydrostatic vertical pressure gradients, which drives fluids upward. And this uniformity of this upward flow condition everywhere along the section show us that it could be the result of the overpressure dissipation, which is already fully dissipated above the red line, but still there is this very small excess pressure which can drive fluids upward. And this result is interesting because, or the from the point of view of the renewability of the groundwater resources, because as I have already mentioned, the topography-driven systems have renewable groundwater resources. Of course, the time scale could be a question, but it has surface recharge areas, while the overpressured system represent non-renewable groundwater resources. And we can say the same about the transition zone. It doesn't have a surface recharge area or any replenishment from other flow systems or from the land surface, while it's the driving force, as I've mentioned, is coming from the overpressure dissipation. So actually in the transition zone, we can say that the groundwater resources are non-renewable. Okay, now which is, so all of the results that I have shown you until now are coming from the basin scale evaluation of hydraulic data. But we still had a question after these evaluations, because based on these interpretations, we couldn't define the boundary of the topography-driven system and the transition zone in the discharge areas, because in the discharge area, both system represents upward flow directions. So by PZ, AZ profiles or hydraulic cross sections, we cannot define the boundaries. And to solve this question and also to analyze the interplay of the different flow systems, we ran 2D numerical flow simulations along the same section that I have showed you. So along this section, just we cut down the lower part, the overpressured part. We only modeled the upper part, the normal pressure conditions, because first we want to analyze the relationship or the interplay of the topography-driven system and the transition zone, and we want to find their boundary also in the discharge area. So in the first step, we avoid the problems with the overpressured system. Okay, here you can see, the geology of the model. I will talk about it in the next slide, but you can also see here the boundary conditions which were defined based on the measured data. Okay, now regarding the geology or the geometry, we have seismic sections along this hydraulic cross section, and also well logs from boreholes. So we can interpret this geological information, and we also created 3 different sections. Now in the first section, you can see that this yellow upward or uppermost layer is the Great Plain Aquifer. It's a regional, actually a regionally unconfined aquifer system. And in the second and third version of the geological model, we divide this regional unit into 3 and then into 4 subunits, and we also analyze the effect of this heterogeneity of the flow systems. And we found that the second model, or the numerical simulation with this second geology or geometry, give us the best results in that term, that these results show the best representation of the interpretation of the measured hydraulic data of the previous hydraulic cross section. Okay, so here you can see one result from the different simulations. Here you can see the Darcy fluxes, hydraulic head differences. I don't have time to explain the details. The main point that actually the streamlines and also the analysis of the hydraulic head differences helped us to separate the topography-driven system from the transition zone, and this red dashed line shows us the actual boundary of the 2 systems. And in the lowermost figure, you can see the interpretation of the simulation results. Again, here the red dashed line shows us the boundary of the 2 systems, and we can see that upward flows in the transition zone are deviated by the topography-driven flow systems in the northern part of the section towards the south or southern discharge zones. And then after the point where the boundary of the two systems run to the surface, after this point, we can actually see that the transition zone approaches the land surface, and we can see the upwelling of water from the transition zone towards the surface. Now that's all about the regional groundwater flow conditions, and I would like to show you two natural phenomena related to this flow system configuration, which can be explained very well by this configuration. Now, one of this interesting phenomena is the distribution of surface salinization, which is a typical natural phenomena in Hungary, in the Great Hungarian Plain. Now, actually, these purple or purple-like colors show us areas where we can find surface salinization phenomena, such as saline soils and lakes and saline vegetation. And all of these areas can be found in those in the discharge areas of the transition zone. So actually, the topography-driven groundwater flow systems can be found in the elevated parts of the basin between the, let's say, the yellow lines. These are equipotential lines otherwise, so Dunatisza interflow, the Nyírség area, and the Maros alluvial fan, which are actually regional recharge areas, which are basically covered by topography-driven flow systems. Then it comes some narrow discharge area of the topography-driven systems, and then the inner part of the basin is actually the discharge zone or area of the transition zone. Okay, and another interesting phenomena which related to these flow systems is are the microbial gas accumulations in the area. Now, actually, this is the same section, just with a previous geological interpretation that I have shown you in the previous slides. And in the middle of this section, we can find the Hajdú-Szoboszló gas field, which is the largest, or at least the second largest gas field in Hungary. And about 1/3 of this gas field is has microbial origin. So, and microbial gases, these are generated in shallow depths at shallow temperature by microbial activity. And we know that these microbial gases need some focusing mechanism which can focus the migration and the accumulation of these gases to form commercial accumulations. And that's why we create an migration and accumulation model in the area. And here you can see this blue rectangle show us the main microbial gas generation zone in the basin, which actually covers that zone where the topography-driven downward flows meet with the transitional zones upward flows. And in this zone, actually, the vertical flow directions turn to horizontal or lateral flow direction towards southwest. And here in the middle of the section, if you remember, here is the boundary of the topography-driven flow systems and the transition zone. So this is the place where the deep originated upward flows can approach the land surface. So this is the due to the regional groundwater flow conditions, groundwater flows turn upward in this zone at first time, and due to this upward flow, the pressure can drop or decrease, and the gas can exhalate it from the dissolved state, so we can have free gas phase which can be trapped in hydrocarbon traps. And yeah, actually we can also find quite large fault zone in this area, which can also help the upward flow of fluids, also water and hydrocarbons. And most of the gas is trapped in traps which related to this fault system. Okay, so that's all about the related phenomena. And finally, I just would like to mention you that what is the significance of these results beyond the area specific significance. Now, of course, on one hand, the question of the distribution of renewable and non-renewable groundwater resources can be interesting in water management. While regarding our further research areas, I can mention our nature-based MAR approach or concept, which was developed, or it's also under development now, by our hydrogeological research group. Now, in this concept, we try to use managed aquifer recharge techniques in appropriate places which can feed groundwater flow systems. And in this way, in case of the appropriately placed MAR installations, we can also bring some water along the flow systems into the discharge areas. For instance, in this picture, you can see a groundwater dependent ecosystem, so we can improve its water replenishment by this method. And related to this concept, I can also mention that our results are interesting from the perspective of ecosystem rehabilitation. You know, now in the European Union, it's quite a fresh and actual topic. We have to rehabilitate about 30% of our degraded ecosystems until 2030. And we would like to use the nature-based MAR concept also for this purpose, to rehabilitate degraded ecosystems. And in these approaches or methods, it's important to understand the flow systems, to know where can be the recharge and the discharge areas of the different flow systems. And as I mentioned, in the Great Hungarian Plain, we have a lot of saline ecosystems, which also need the salt content of the deep groundwaters, which can flow upward in the transition zone. So that's why our results can be significant or important also in ecosystem rehabilitation. And that's all. Thank you for your attention.